We got 4 people.
Oh, I just can't read. Hey, Chad, I see you got my email. Chad's our new member from Eufaula, is that right? He's got himself muted, but that's good.
Can you mute your computer?
I've muted my audio output.
All right. Okay.
Turn him on.
I can't turn him off. I have no control over his system.
Nope. I'm working it on my end.
He's working on that end. Isn't this wonderful? Anyway, oh, we got some new people. Anyway, I'm John Land. I'm the president of the club. And this is James Taggart. He's our observatory director. And I see Crystal made it. And the rest of you hiked in a mile to get here. So who's our young man over here? I can barely see. What's your young? Well, I guess I'm not. I thought, no, I'm sorry. I thought that, never mind. I can't see. Got a light in my eyes. Anyway, we'll try to have our program here. If you're a member, okay, raise your hand because I want to know how many we got. Steve, will you stand up and do a count for us? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did you get them? Okay. Well, we'll figure this out. One of the things we need to do is make a vote tonight, but we may have to do part of it by email. Okay, welcome to Astronomy Club of Tulsa, April 14th. I guess you can see that up there. Is he going to advance this or am I?
He will.
Oh, that is amazing. Okay. Well, here's our events. Going to talk about our upcoming events, observing nights and such. We have a short business session. I'm going to talk about the Mid-States Conference. It's going to be right here, June 9, 10, and 11. And then Brad is going to do his program and breaking news. I hope I haven't stolen his thunder. Okay, we got 2 more people, 3 more people. All right, you made it. Then I'm going to talk about some interesting things that we missed because it was cloudy. The Northern Lights were seen in 32 states on the 23rd and the morning of the 24th of March. And then our keynote presentation is about the Nancy Grace Roman Space Telescope that's going to be going up in 2027, if I remember right. So next slide, Mr. Okay, we have an observing night tomorrow night. I've got a lot of people signed up, but the weatherman's not being very nice. There's a cold front coming through the middle of the afternoon. So if it is clear, you're going to need your jacket because it's supposed to be cooler and windy. We'll just have to see what it does. It's Oklahoma. We have our members night on 21st. And if I believe that's right, Brad will tell us more. That's pretty close to the, is it the Leonid meteor shower? There's meteor shower coming up. Not Leonid, Lyrid. Lyrid, yeah. Yeah, anyway, there's a couple of meteor showers in late April, and that'd be pretty close to when they're coming up. So we might get to see some of those then. Then we have a member night on the guest night on the 12th. It's on a Friday. When we get deeper into the daylight savings time, we can hold them on Friday, and then we have the option if it gets clouded out and the weather's better on Saturday to go ahead and postponed to Saturday. So that'll be the same thing we'll do on the 21st. If the 21st is cloudy, then we have the option to go ahead and be open on the 22nd. So that's the nights that are coming up. And of course, you can see that oh, that's not me, thank goodness. Anyway, same ringtone. Okay, next one. So James, you get to come up and talk about this, and we'll take a hand vote here in a minute.
Yes, what we're wanting to do is add handrails to get up to the top of the observatory. I called, I think it was a total of 7 different contractors, got quotes back from 2 and only got one of them to actually come up and do a final quote. This is the company that was willing to do it. And they're willing to, if we agree to it all, they can start next week, and it will be a continuous rail for that entire staircase.
So
Make
if
it a little easier to access for everybody.
you've been to the observatory, there's a spiral staircase that goes from the bottom floor up to the dome floor, and there's no handrail there. And it's dim red lights, and we're used to it, but our guests are not. So just for safety's sake, we discussed maybe doing it ourselves, but the opinion was it'd be better to have somebody do it professionally. And so James has been diligent to try to get somebody to make a bid.
Yeah, getting help up there is a little hard sometimes.
We're kind of way out. People don't want to come out that far. So the bid price is $2,560.
Yes.
And it's from Tulsa Staircase Company, and they have been out.
Yes, yeah, they've come out. That's approximately like a 30-some-odd foot railing. With the railing itself is wood, but the brackets are all metal.
So it'll be safer for everybody concerned. And we got our big convention coming out, so we want to look nice for that. So we need a vote, and we'll take a vote on people with Mr. Brad.
Sure.
Is this a estimate or is this a hard bid?
This is a hard bid.
Okay.
Yeah, this was originally their guesstimate, and then I made them come up Monday, and they walked back through and said, no, we're going to stick with the number we gave you.
Okay. How far will it extend away from the wall?
We're going to try to keep it as tight as possible because that is just a narrow hallway. I think the only part that'll stick out a little bit is where the wall actually recesses back in. There's that flat spot, the landing halfway. That wall is actually about 6 inches farther back than the rest of the wall. So it will stick out a little there, but it'll be one continuous strip.
Oh, instead of pieces, it'll be a good.
Correct.
Oh, okay, that's good. That sounds like a good deal. So I should have had a motion to open up for a business meeting.
I make a motion.
Brad made a motion. So can somebody take some notes? Tamara seconds. Skip, did you get that? Don't know if he can hear me. Somebody make some notes.
John, who made the motion?
Brad and Tamara seconded it.
Thank you.
Skip is our secretary, but he's under the weather tonight. So we can see everybody who's here to vote. We'll have a standing vote. Okay, if you're in favor of approval, you have to stand up so we can count, because I'm not good at counting.
You're just making it stand up.
Yeah, we got to exercise it. Okay, James, you helped out.
Got 17. Oh.
Richie, we need you to vote.
19. 19 with Richie.
19 with Richie. And we got Skip online. And we had some other board people vote.
We have to have 60% like all the bond issues.
No, we had to have a quorum, but we've got some people online too. So I think we're all right. But All right,
Hey, John, what was the
somebody
vote?
make a motion to close the business session.
Make a motion.
Hey, John,
Brad
what was
made
the
the motion
vote?
to close the business session. Is it Don? David Taggart. All right. Thank you. So we'll get with our treasurer and get that going pretty quick. Thank
Hey,
you.
John, who were made the motion and seconded the motion to close?
Brad made the motion and David Taggart made the motion to close, second to whatever, seconded the motion. That's James's dad. Thank you, Skip. All right,
You're well. Hey, John, what was the result of the vote? Did you have a count or just a majority?
19 standing, and you would make 20 if you'll vote.
Yes, I vote yes.
Okay, and we got some yes votes from Mike and Jerry is a mother online, so. All right. Next. You should have already gotten an email, unless you're a brand new member, about the Mid-States Convention coming up to June 9, 10, and 11. It's going to start on Friday afternoon. We'll have a Starbecue from Oklahoma Joe's, and then a short program, and then we're going to go out to the observatory and let our members and guests see the observatory, just sort of have an observing night. It's a third quarter moon, so it's not one of those all night things like we usually do, but it's kind of to show off our facility and welcome our guests at an observing site. And then we'll come back here on Saturday morning and we'll have some presentations. And then we'll break for lunch. And at the lunch hour, James, can you pull up that other website I was showing you? The Misrule 2023. Not James. Dan.
Yep.
Get my brain right.
Is there a deadline for signing up for it?
Yeah, yesterday. No. Yes, we need them signed up. I believe it's the 26th of May, but we really want our local people to do it sooner. So we're kind of having we've got to put in we've contracted with a catering company and we have to tell them how many people are going to come to the banquet. And then we also have to make an order for the Friday Starbecue. And we're going to have kind of like little in the morning, little juice and fruit stuff in the mornings that people arrive. So kind of have to are we going to prepare for 60 or are we going to have 100? We're hoping for a break even around 80. So as soon as you can get registered, we'd really appreciate that. So if you'll click on the speakers real quick, Dan. There's our keynote speaker. He's come from the University of Arkansas, and he's going to tell us about multi-messenger astronomy. Most of you have been listening to about the last year and a half, these gravitational waves. Einstein predicted that when gigantic objects like black holes and pulsars merge, that it would make waves of gravity through the universe. And we're finally able to detect those. So it's like having a whole new window to what's going on in the universe. Initially all we had was our eyes, and then we had the telescope. And then finally in the 30s, we had radio telescopes. And then throughout the 60s and 70s, we got other wavelengths like infrared and ultraviolet with the satellites. And here's a whole new window to the universe. So he's going to talk about that. Scroll on down a little bit. Peggy Walker is the regional representative to the league. She's going to tell us a little bit about Misrule in the past. Scroll on down. John Moore is one of our members. He's kind of interesting. what was it, 19th? It was in July or late June. The moon went in front of the star Aldebaran up in Taurus. But from Oologah, it just skimmed along the edge. And so it blinked in and out behind the mountains on the ridge of the moon. And several of us went to Oologah, but John he lived over by Keystone Lake, and he got some recordings, and he's really gotten into this. And so now he is with the International Occultation Timing Association, and he's been to South Africa and South America and other places with some NASA efforts to, you remember when we went to that object beyond Pluto? I can't remember, Ultima Thule is what I remember its name was. And they were able to catch it in an occultation and figure out its orbit and stuff. So he's going to tell us a little bit more about that. Going down, oh, this guy Brad, he's always got good things to do, and he's got a guest speaker going to talk about obsolete and alternate constellations. And our guest Dan there is going to show us some of the stuff that his students have been doing. And this gentleman's from Bartlesville. They've been working with Osage Hills State Park there, making it a dark sky friendly site. And the next one, there's a group that's building a portable observatory here in Tulsa, and they're going to have it in our parking lot that afternoon for us to look at during the lunch hour and tell us a little bit about it. So, and then we've got some other speakers, but we don't have them up there yet. But registration, you can see that's there, and you can click on it and get registered. Brad.
I had a question out in the lobby that you might want to discuss, and that is there is a reasonable charge for the convention itself, and then some of the snacks that are provided, but the meals, you have to sign up for those individually at a extra cost.
Right, you have to. We're paying rental for the use of the facility here, and we also have to buy all the miscellaneous things like water and snacks and stuff throughout the convention. But the lunch, you either can sign up for lunch. Mike's working on a pizza and sandwich menu. And then we have our keynotes banquet that night. And Kathy just walked in, has a great menu. It's a Italian mixture of Italian half and half. And we got the menu updated finally, so you can look at that. And I already told you about Oklahoma Joe's barbecue, but those things you need to pay for separately, right? Any other questions? Okay. All right, we can go back to the program.
Brian.
Brian. Somebody had a question?
Oh, sorry, it was me. I was just trying to move screen.
Oh, okay, scroll down one. Our administrative team of about 9 people has been really busy since December, but we cannot run this thing with 8 or 9 people. So we need people here who can come no later than 1 o'clock on Friday. Help us set up tables, help us get ready for registration. That opens at 3. Welcome the guests that are coming in that local are from out of town. We've already got 15 out of town as far away as Illinois and Texas, Missouri up from St. Louis area coming. I've heard from Kansas City that they're coming. Explorer Scientific from Arkansas is going to come and be one of our contributing to our door prizes. So at an astronomy shop in Central Illinois, it's going to send us some door prizes. I wish I could remember the name of it. So we need our people to help. And James is going to need people out at the observatory getting ready and welcoming the guests that night too. So we'll be sending out sign up stuff and calling for volunteers. But like I told Tamara, we'd like you, if possible, to get registered by early May. So we got an idea how many people are going to show up. And I need to do that too. I just haven't got around to it. All right, next one. Okay, Mr. Brad. I'll let you sit here where I am so I can see your lovely face.
How am I gonna see my?
It's on the screen.
Okay.
Oh, I gotta get up here.
Go ahead.
That may take a while.
Okay, it's called transitioning for a reason. You might have thought that I had a misprint in the article, or if you look at it here in just a minute. Is that the first slide you have? Oh, that is the first slide you have. Yes, because I wrote this presentation quite a while back, and there's been a lot of things happening lately. This happened today. We sent out blasted off with a new spacecraft to go to Jupiter that's called JUICE, which stands for Jupiter Icy Moons something or other exploration. And what I wanted to do was try to catch it, try to image it on its way out. And so if you could click on the link, or if I need to, which one? Okay, there we go. This is a couple of images that I took of it this afternoon. It was night in Perth. Perth, Australia is where this telescope is located. And after the spacecraft took off and separated from its rocket, which you also see there, it was on its way to Jupiter eventually, but I caught it on the way out. I think we've figured out that the brighter one is the rocket body, although that's still under discussion when I came to this meeting. So we'll find out later which one was which, but that is JUICE on its way to Jupiter. And then if we could go back to the, yeah, you're probably going to get hit with something every time you go to YouTube. Anyway, that's what the next slide is about. JUICE launched today. We'll visit the icy moons of Jupiter. You can kind of see a small picture of it there. I couldn't really find any good pictures of it. It's already extended its solar panels. That's why it's bright enough to even take an image of it. And it was about, I think it was close to 200,000 kilometers from Earth when this picture was taken. So it was quite a way, or almost the distance to the moon, about 2/3 of the way. It wasn't going towards the moon, but that's the distance that it was at. And it was still about 11th magnitude. So it's a bright little thing, and it's got a bright rocket too. It was a fairly large rocket that launched it. I can't remember which one it was, but anyway, I thought that was interesting. And hopefully it will arrive at Jupiter and do what it's supposed to do. It's going to go into orbit around Ganymede, which is one of the big 4 Galilean satellites of Jupiter, and study it closely. And that'll be the first time that we've ever had a satellite that has gone into orbit around another planet's moon. We go in orbit around our moon on occasion, but that'll be the first time we've orbited another planet's moon. Okay, next slide, please. More breaking news. I've been working on putting together solar eclipse observing. Hopefully it'll turn into a program at some point. But when I turned in my rough copy, they said, let's go ahead and make it live. So we have, with the Astronomical League, if any of you do the observing programs, which, you know, everyone that's a member of this club is a member of the Astronomical League. It comes with the dues that you pay. You're automatically signed up. And they have around, I want to say 80 observing programs now. This one is for the next 2 solar eclipses. You probably have heard about these already, but just to remind you, we have an annular eclipse in October, and we have a total eclipse next April, and both of them are close to Tulsa. You may have to travel if you want to see both of them at their best, but for instance, the total eclipse, I know that it passes right through like the Tallahena Drive area, so it's pretty close. We'll look at a map actually here in a minute. There it is. And as you can see, it kind of clips the center line, which is that white line in the middle, kind of clips the southeast corner of Oklahoma. And then the grayish green band
is where you can see totality. Of course, you want to be as close to the center line as possible. But if you'll notice, this passes almost through Dallas, almost through San Antonio, almost through, the heart of Texas, the hill country. Austin's just inside the limit. So, and further on up, it goes up into, the Midwest. And there's quite a few. It's a lot like the 2017 total eclipse, except this one's a little longer, and it's actually going to be visible if the weather holds out, visible to more people. So really looking forward to that. The annular eclipse, I forgot when I put this map in, John, I forgot the other map had the annular eclipse track, but it's basically the sort of a opposite of this from the northwest, like around Oregon, down through New Mexico and into Texas, and it actually passes through San Antonio too, so they get both of them. Lucky them. Okay, next slide. So that's all of the breaking news for now until the end. But here's the actual observing session that we were going to talk about, and that is, I called it transitioning. Transitioning is training yourself to go, not only transitioning to the spring sky, but also training yourself to change gears sort of from what we look at in the winter sky to what we look at in the spring sky. In winter, we usually look at galactic objects like open clusters, reflection nebula. I'll give you, the Orion Nebula as an example. The Eskimo Nebula is a good planetary that we look at. And those are wonderful objects, and they, everybody wants to look at those, and we often do, but they require a little bit different approach to looking at them than some of the objects we look at in spring. Because in spring, where we are in the Earth's orbit, we tend to see the night sky with the Milky Way flat to the horizon. So we're looking up out of the Milky Way and looking at other galaxies. And what that does is, when you're looking at a galaxy instead of a galactic cluster or something, your eyepiece, you may choose a different eyepiece, different filters, etc. So your equipment may change a little bit. And also we need to sort of train our eyes to look at something different. Next slide. So if you look at some of our winter to spring objects, the article that I wrote that some of you may have read, everything in there is my own, but I want to be clear that on this presentation, the sketches are my own, but the images are most certainly not done by me. But I wanted to use those so you could actually see a picture of something. This is my attempt to sketch NGC 2403, which is a really nice galaxy. I believe it's in Camelopardalis or Draco, somewhere up there in the northern sky. Very easy to see in spring. But you'll notice that the picture shows it much better. And if you have a larger telescope or use higher power, you may see a better picture than what I sketched here. But that galactic object it's very tenuous. Most galaxies are sort of, they call them faint fuzzies for a reason. They're typically faint, and they just look like a fuzzy glow. There's oftentimes not much detail to them unless they have a dust lane or a bright nucleus or something, or a companion like M51. Most of the time they're sort of a glow that comes in a shape either round or flat, but not a lot to them. Okay, next slide. And when you compare that to some of the things that we look at in winter and summer, much better for globular clusters, but globular clusters are often pretty easy to tell what they are. They look like a dirty snowball, almost like a comet, except sometimes you can resolve stars around the edges, especially if you have a larger telescope. But most of the time, a globular cluster is going to be a very condensed, brightish object. And what you want to do with that is you may not need a lot of power on it because it will contrast against the black sky pretty easily. But you, like I say, you may want, the largest telescope you have, you may want to get that light bucket on it and try to see your globular cluster as well as you can. I wouldn't say on either one of those objects you would need to use any kind of filter, like an O3 filter or anything like that. But we'll get into that in a minute. So next slide. So here I kind of switched gears on you and started off with the galactic cluster. This is Messier 37. This is an Auriga, and it's one of my favorite open clusters. And with an open cluster, you don't really have to work too hard at those. Most of the time, the only problem with an open cluster is just discerning it from the Milky Way that it may be showing up against or something like that. M37 shows up very well. You can tell that it's a cluster. You don't have to try to pick it out of the background or anything, but it is looking at you want a wide field. And so you're going to want one of your, bigger eyepieces that give you the widest field you can get. And you're looking at typically bright stars that are usually completely resolved. Next slide. Compare that to galaxies like NGC 2387. This one is very faint. Might have picked a different one, but with galaxies, a lot of them are going to be very faint. There are some showpieces certainly out there, especially in Virgo. Some of your Messier galaxies in Virgo are wonderful, but a lot of galaxies are not very easy to see. This one was pretty difficult even in my 22-inch scope. And you'll note, I put a note on there that 2 of the galaxies I drew as field stars were actually, field stars were actually galaxies. So, another problem you may run into when you're in Virgo and looking at galaxies is, which galaxy am I looking at? There's quite a few there. They all kind of look the same sometimes. And so you may have to try to identify which one you're looking at. Okay, next slide. So what do we need to do this? How do you transition? How do you train yourself to change from one type of object to another? Well, winter objects are typically bright and larger than galaxies sometimes, and they may sometimes be completely resolved. If you're looking at an open cluster, you may be able to see all the stars in it. There's no fuzz to it. A wide field image, should say, and eyepiece are okay. As a matter of fact, they're often preferable because you're trying to see a big object and you don't need to push the power in order to bring up the contrast. But meanwhile, your spring deep sky objects are usually fainter and can be smaller. So you'll want to increase the power, use a small or a lower size eyepiece for higher power to get that high contrast. And averted vision, if any of you are unfamiliar with that term, is kind of looking off to the side instead of staring directly at the object, looking off to the side in your eyes and looking for shades of gray. Oftentimes that's what's going to tell you you're looking at the object is just it's gray compared to the black background, and there's not a lot of contrast to it. It doesn't stand out like some of your winter objects do. Okay, next slide. And the reason for that is because our eyes are built the way they are. They have cones in the middle, and the cones are kind of like the RGB system for your astrophotographers. That's where we pick up our color, but at the same time, you need more stimulation of the cones. In my little joke here, you have longer subs. You can't get the same amount of photon information from your cones in the same amount of time as you can with your rods. The rods are much more sensitive. There's a lot more of them. I think the number was something like 2,000 cones and 20,000 rods or something like that. It's a big factor, a big change. And the rods are off axis of the retina. The cones tend to be right in the middle of your eye, and the rods surround the retina. So that's why you look off to the side slightly, and that way you get photons to your rods, which are much more sensitive to light, but they don't give you any color information. Okay, next slide. And then I wanted to bring up sketching. Next slide. And the reason is because if you don't image, maybe the best way to record what you're looking at is to sketch things. You can still have an observing notes or journal. You can put the notes right there with the sketch if you want to. One reason that you want to sketch things is it really forces you to stop and look at the object. I know that when I first started in astronomy, I didn't really pay much attention sometimes. If I was looking at a galaxy, let's say the sombrero, I knew it was supposed to look like a hat. And as soon as I figured out that I was looking at it I was kind of done with it. I didn't take the time to really look at the dust lane and look at the other side of the nucleus or any of the details that are available. But sketching forces you to look at it, sketch it, go look at the sketch, go back and say, oh, wait a minute, that, I got to change that. It forces you to look at the object and really pay attention to what's going on. It's not necessary to be artistic. If you've seen any of my sketches, you'll know that it's absolutely not a requirement. And it captures a lot of information for use later. If you're star hopping, you can record the pattern of field stars. I don't think I put this in here, but the other thing, when you record the pattern of field stars, if you have any doubt that you saw the object, you can go to an image. Can we go back about 8 slides, I think? Oh, that's it right there. So I don't have it turned correctly, but you can almost see that there's a line of 3 stars that are near this galaxy. Yeah. And then on the other side, if you can use your pointer, they kind of go a different direction, but then that triangle's over there too. So this kind of tells me, yeah, I probably did see it, because I've got a field star drawing that shows me, even though it's not inverted like the view in my eyepiece is, that shows me that the field stars kind of match what's in the official image of it. Okay, can we go back to the slide I was on? Yeah. Also, if you do find a unique feature or memorable detail, something you hadn't noticed before, and maybe you're looking at a galaxy that you looked at last year, and this year you notice, hey, there's something strange about the galaxy. Let me draw this. You might discover a supernova in another galaxy. You never know. Or maybe you just have the enjoyment of seeing it a little better and noticing a detail you didn't notice before. And then you can draw and describe differences when you change power, or if you use a filter, or if you use averted vision, or some of these methods. You can record for yourself what effect they may have on the image, and tell yourself later on, if you want to go back and revisit that object, hey, you might want to go ahead and use a filter on this one because it brings out this detail or whatever. Okay, next slide. The other breaking news, this was supposed to be the only breaking news, and then everything else happened. The Astronomical League also has observing challenge number 8, which is Galaxies 2.0, if you bring that up. What this is they have pretty much every season, they have a observing challenge, and this one is looking at galaxies. Obviously, that's like we're talking about, that's kind of the hot thing in the spring. And if you go down just a little further, there is another link, probably the next paragraph. Oh, there we go. The list can be found here, is down at the bottom right. Yes, can you punch that? Okay, so what they want you to do is look at 10 of these 20 galaxies, and these are all pretty well-known galaxies. For instance, Caldwell 7, the very first one that we saw my sketch of, that's in here. It's in Camelopardalis. Okay, that answers that question. But you can see that at least 10 of these are probably ones that you could look at fairly easily if you want to do this challenge. And now I think you have to do an outreach, some kind of outreach event for this, or outreach, not necessarily an event, but just do something with outreach, talking about looking at galaxies. So, for instance, if you go to Skip's, I believe it's his niece is having their Girl Scouts are having a viewing at Ulaga in a couple of weeks. If you go to that and bring your telescope or whatever and talk to the young ladies that are there about galaxies, and that would count as an outreach event for this challenge. Okay, next slide. And that's pretty much it for this observing session. Don't forget, Mercury and Venus and Mars are in the evening sky. Mercury's kind of leaving fairly soon. I thought this was going to be a talk given a little earlier in the month, but it's still there for a little while. There's the meteor shower, the Lyrid meteors peak around April 23rd. just to let you know, last look at Orion and all the gems of winter, they're all definitely leaving. Don and I were observing the other night, and he said, well, it looks like we're about to lose Orion, and he's right. But that brings up the galaxies. We'll soon have the galaxies in Virgo to look at. And that is the end of the session until next time. So does anybody have any questions or comments? I don't know. Yeah. Go ahead.
That picture of juice,
Uh-huh.
and there was like, oh, it was two lines of video.
Yes.
There are like two objects going, or?
Well, what's going on with that is that's a 60-second exposure. So since it's tracking the stars, they are moving. I mean, that's the motion in 60 seconds of the spacecraft and the rocket. This field is about 1/2 degree wide, so that's about the size of the moon. So the objects are moving, and this isn't the entire field. So they're moving. I would guesstimate about 4 or 5 minutes of an arc in that 60 seconds. Other people, sometimes you'll see where people will track on the object and it'll make the stars streak like that. But because it's moving against the starry background, it shows up as a streak. Yes, and usually the dimmer streak is the spacecraft. The rocket body is actually bigger and not more reflective, but just because it has more surface area, it ends up being brighter. Do you know what that is? Okay. Anyway, thank you.
Thank you. Oh. Go back to our regular program a moment. I'm going to set this down. How many of you have seen the Northern Lights? 1, 2, 3, 4, 5, 6, 7, 8. How many of you have seen them in Oklahoma? 3. They have been visible here. I remember the first time I saw them, I had some students out at Indians. Oh, what's the name of that? Timberbrook, east part of Broken Arrow. And there was a pasture there, soccer fields thing, and we had telescopes set up, and one of the kids said, there's a fire out north, and we saw these yellow pillars going up, and it was just, it turned out to be the Northern Lights. So I vaguely remember seeing the green when I was a kid in elementary school up in Bartlesville, but I've seen them at least 4 times here from the Tulsa area. Went on a cruise to Alaska, didn't see anything. But anyway, so this was the 23rd. Unfortunately, we were clouded out. I think it was even raining here. But this gentleman took a picture of it from, he said, southern Oklahoma, Paul Smith. And they kept getting more and more information in. And at least 32 states, including, we can see down there in the Florida Panhandle, they were able to people to send in images of it. And another thing you'll notice is that the top half of the United States is green and the lower half is red. And the reason is that the lower part of the lower altitude, there's a scientific reason for which molecule is being stimulated. But the nitrogen is the green and oxygen, I think, is the red.
The other way around.
Other way around. Okay, nitrogen, whatever Brad said. But the green is lower than the red. So if you're too far south, all you can see is the top of the aurora. But I've actually seen yellow pillars going up in it. So this was someplace here in Oklahoma. So next one. Our solar cycle is getting really active. I like to watch the space. We won't click on it because we've got other things to. It's called spaceweather.com. And every day they have a new image from the Solar Dynamic Observatory of what's going on the surface of the sun. And you can link over and see it in all different website wavelengths if you like. But the one on the right there shows you the solar activity for cycle 23, which ran from 1995 until about 2005 or so, and it was pretty active. And then the sun almost quit in 2009. I mean, it was like months and months without a sunspot. And then it came back and we had a really low solar cycle in cycle 24. And all the experts say, well, this next one will be low too. In fact, back there in cycle 24, they were hypothesizing that the sun would quit like it did back in the 1700s. There was, I don't know how many years it was, they called the Little Ice Age. But this one has really taken off. We're not even close to the peak yet. But an article just came out last 2 days, a new way to predict the solar cycles, linked to when the magnetic field of the sun flips from south on the top to north on the bottom and vice versa. And so they're predicting that this one will flip sooner, perhaps later this year, or early next year. And then the peak of the activity will be early. You know, theoretically, the solar cycle is about 11 years, but it can be as short as 9 and long as 12 or a little bit more. But I'm a little bit skeptical because I've always seen all these predictions and they never seem to pan out. So we'll see if this one works. But watch spaceweather.com and you can see what's going on. All right, next one here. Speaking of eclipses, Brad already mentioned, let me lay this down. We have 2 of them on a Saturday, October the 14th. We're going to have a 78% eclipsed here in Tulsa. It's an annular eclipse. You can go down to San Antonio and see the sun is just, the moon's not quite big enough to cover up the sun. But our club has ordered 400 of these. I was hoping to get somebody to help me put them in envelopes tonight. So if you want to volunteer, you are welcome to do that. But they're eclipse viewing things. You can put them over your eyes, or what I recommend they do, I'd use them for children. I put them behind a thicker paper plate and just cut a hole. That way they hold the whole thing over their face and their face is protected. But they're going to have a webinar like we're getting ready to watch on Night Sky Network on the 27th about the scientific magic of total eclipses. Anybody want to guess what eclipse that image is from? I heard Brad chuckling. That's the one we had in 2017 that I got clouded out for. But anyway, if somebody wants to volunteer, I have some of these you can help us get ready for. We're going to start selling them in bundles of 5. And I hope that we'll have at least 2 places to have the public come and view the eclipse in October. Sorry. All right, next one.
John, are you going to have those at the convention?
Yes. But they're going to have to buy their own.
Yes.
We're going to give a few of them for door prizes, but I'll tell them how to buy it. We're kind of using this for our club. Nancy Grace Roman is considered the mother of the Hubble. She was the Miss Space Telescope from all the late 90s on. First woman to get into the administrative ranks of NASA. You can read all about her. So we have a new space telescope called the Nancy Grace Roman Telescope. And she actually visited Broken Arrow schools with a group of scientists in November 1999 and signed a couple of images of the Hubble Space Telescope. I gave one of them to Abby Bolenbach. Some of you remember Abby, that was real active here for a while. But I couldn't find my other one, or I would have brought it tonight. But I'm going to quit talking, and we're going to bring up the program here. This is another one of these night sky network things.
Gonna need you to mute the Zoom.
Mute the Zoom. Your turn, James. I can't do those things.
No sound on Zoom.
Skip, you said you still can't hear it?
I'm not hearing the audio from the program, no.
Thank you. I'll figure it out.
And she did other things as well. She helped set foundations for making sure that the data that we get from our telescopes is public, right? So it's not hidden to just scientists and so on. And so she really set the way for opening up science at NASA for not just scientists, but for everyone to appreciate what we're learning from the universe. So here's a diagram to bring everyone up to speed on the history of major space-based missions for NASA astrophysics. These come out of what's called decadal surveys that happen every 10 years. And the astronomy community, the scientific community gets together and prioritizes what they think needs to happen. And then what has happened, from that is NASA has worked with the science community to create a space telescope to address those science needs. And so all of these telescopes on here have come out of that process, this community-based process from the astronomy community to essentially address the current scientific needs by building space telescopes. So 1990, Hubble was launched. In 1999, the Chandra X-ray Observatory was launched. 2003, Spitzer was launched. And of course, we all know on Christmas Day 2021, James Webb Space Telescope was launched. And like I said, the next big flagship to come is the Nancy Grace Roman Space Telescope, which is going to be launched by May of 2027. I like this quote on the screen, by the way, too, from Nancy Grace Roman, which basically gets at this idea that scientific research and engineering is a continuous series of solving puzzles. So as we have these space telescopes explore, observe, collect data from the universe, we get fundamental new questions from mysteries of what we see. And that drives exploration, design and exploration with new technology to try to answer those questions. But inevitably, that new technology, those new observations provide more questions. So we need to design new technologies, new instruments, new telescopes to try to address those. And that has really been what has been driving the development of these telescopes. And that is no different for the Nancy Grace Roman Space Telescope.
Ringing in your ears. Can cause total brain shutdown in under 2 years.
So this sort of encapsulates a comparison between the Hubble Space Telescope, the James Webb Space Telescope, and the Nancy Grace Roman Space Telescope. And the big takeaway here, I think, what I want you all to come away with is that these telescopes all complement each other. None of them replace the other. Now that we're having Roman or Webb, it's not like Hubble is not needed. Hubble is very much has its own thing that cannot be duplicated by Roman or Webb. And so some of that information is conveyed on this picture here. One is on the very far left, you get a sense of the size of the mirrors of the telescopes. Now, as a reminder, right, telescope mirrors are incredibly important. I don't have to tell you all this. You all know this as well as I do, if not more. But the larger your mirror, essentially, or lens on a telescope, the larger your collecting area, right? And so if you have a larger mirror, you can collect more photons from objects in the universe. It allows you to really see, a larger mirror allows you to see fainter objects in the universe. So you'll notice on here that Hubble and Roman have the same size mirror. And so they have the same collecting area. And so that's why I say, that's partly why I say that Roman is going to produce Hubble quality data. Webb has a larger mirror. So what that's really allowing is for Webb, it's going to see much fainter. It's more sensitive to seeing the faintest objects in the universe, right? Particularly in the infrared light. And so that's why one of James Webb's big science goals is to find, the first galaxies in the universe. So look back really far in the universe to find the most distant galaxies, the first galaxies. They're going to be incredibly faint to do that work, right? Because they're so far away light spreads out over the distance of the universe. So they're incredibly faint. You need a big mirror to try to do that work, right? So I think Webb will likely have the record holder, as we're currently seeing, being broken almost every day, it seems like, but the record holder for the most distant galaxy, for example, discovered. Now, if you go down to the wavelength part of this image here on the bottom, right, these are the essentially the energies or wavelengths of light, the colors of light that each telescope can collect. And we don't show all of the types of light here, right? We don't have X-rays or so on, but we have the three types of light that these telescopes can observe: ultraviolet, visible light like our eyes can see, and infrared light. And you'll notice that Roman kind of covers what Hubble and Webb can do. Roman is really situated in the near infrared and a little bit of visible. Okay, Webb really takes you out into the mid infrared to near and mid infrared. So a broad look at the infrared universe, that's really up Webb's alley. Hubble is critical for our window into the ultraviolet universe, right? So Hubble also, of course, continues to do great work in visible and near infrared observations. But in addition, it is our one really high resolution window into the ultraviolet universe, and will continue to do so for the foreseeable future. Now let's get up to the top right. Here's the field of view. Again, how much of the sky the telescope's cameras can see at any one time. And you'll notice Webb and Hubble down there. That's their sort of field of view. That's their eye on the sky. And then you see this shape, which is the Roman field of view. And that Roman field of view, which I'll talk more about in upcoming slides, that shape has to do with the number of detectors stitched together to make the camera. But Roman is a very different kind of telescope from Hubble and Webb. You'll notice Hubble and Webb say targeted observations. For Hubble and Webb, they're really meant to target an object or a region of the universe and study it in tremendous detail. Hubble and Webb each have 4 science instruments with multiple modes and all sorts of ways that you can observe the target. And so if you want to know every detail about whatever you're looking at, it's a galaxy, say, you might want to use Hubble and Webb to do targeted observations to learn everything you can about that target. Roman is a survey instrument or survey telescope. Roman, with its large field of view, will allow it to snap large pictures of the sky in the near infrared. In addition, Roman is a very fast telescope. So Roman has incredible speed, which will allow it to map large portions of the sky. So what Roman can do faster than Hubble and Webb is move its pointing to a new patch of sky, take an image, move, take an image, move, take an image. So the large field of view, in coordination with its speed, will allow Roman to get Hubble quality data across large patches of sky.
This changes everything we know about what really causes toenails to be thick, discolored, crumbly, and cracked.
All right, so I'm going to go through quickly some facts and figures for the telescope. I do put on here a nice interactive you can explore yourself if you go to this page that our Goddard colleagues have set up. This will tell you, this interactive will explain the hardware of the telescope. So I'm going to talk mostly about the science for Roman, but if you want to know more about the hardware, I encourage you to go to this site. But just some basic facts and figures, right? The camera is, the main science camera is a 300 megapixel camera. It has one advanced coronagraph, which I'll talk about in a minute. Its primary mission is scheduled for 5 years. Of course, after the 5 years, as typical, NASA takes a look at the missions and at any mission after its primary mission is over and determines if it wants to do an extended mission and continue to do science. But its primary mission is for 5 years. It will be at Lagrange Point 2, which is a location about 930,000 miles from Earth. It's the same general location that the James Webb Space Telescope is located, and it's beyond the moon. So it's almost 1 million miles, and it's beyond the moon. But it trails with Earth as Earth goes around the sun. So it sticks. It doesn't trail, but it sticks with Earth as Earth goes around the sun. So but that's what Roman and Webb both do. The primary mirror is 410 pounds, which sounds like a lot, and it is a lot. But one thing to note is that's about 1/4 of the weight of the Hubble mirror, and the Hubble mirror is the same size. So there have been some technology advantages there in terms of being able to more cheaply get it off the ground and so on. All right, so I'm going to quickly go over the two main Roman instruments. There's the wide field instrument, which is the main science instrument, and there is the coronagraph instrument, which is a technology demonstration instrument. So we'll start with the wide field instrument. This is the primary science instrument for Roman, and so it will allow for survey-style observations. It has 18 near-infrared light detectors, again, a 300 megapixel camera, about 200 times Hubble's infrared field of view. It also allows for 2 spectroscopic capabilities, so if you want spectra, it allows for that as well. And you'll notice on the lower right of your screen there, that snapshot of this animation, that is, those 18 squares are the 18 individual detectors that essentially stitch together, work together to make one large camera, this wide field instrument. And so this is really the power, right? So the light from whatever you're observing goes through the optics of the telescope and then gets, of course, projected down onto these 18 detectors. And then the coronagraph instrument is a technology demonstration instrument. It's a first of its kind design in space. I think I can play a little video here. It's a first of a kind design in space. It is meant for direct detection of faint exoplanets. Now, the way a coronagraph works, as you're seeing on this video on the screen, is you essentially take a physical mask and you put it in front of the light coming from a bright star or a bright object, whatever it is, a bright point source in the sky like a star. And you essentially mask out the brightness of the star so that you can try to see faint exoplanets going around that star. It's very similar in my mind if you ever drive around on a dark night, or you're walking around on a dark night and someone with bright headlights comes at you and you put your hand in front of your eyes to block out the headlights so that you can see what's going on around you, right? You want to dim that light that's blinding you so you can see what's going on around you. That's basically what a coronagraph does. It blocks out the light from the star so that you can see what's going on around it. And by doing that, you can start to pick out perhaps some planets going around that distant star. Now, why this is a technology demonstration is that there are some technologies on this coronagraph that have not been in place in a space-based telescope before. Most notably, the deformable mirrors that are in the coronagraph instrument itself. So much like adaptive optics systems on Earth-based telescopes will have sort of changed the shape of the mirror slightly to overcome the atmospheric distortions that cause starlight and other things to sort of twinkle, right? In space, you have these distortions that are coming from the optics that are trying to block out that central star. And so you can use these sort of adaptive optics, if you will, or these deformable mirrors to change shape in real time to overcome that. And what that does for you is it further suppresses the starlight of that central star so you can see even fainter planets. Why this is a technology demonstration is for that reason, but it's also for the reason that the goal here is we want to get part way to being able to, in future missions, observe Earth-like planets at Earth-Sun distances around other stars, right? This coronagraph is meant to get us partway there. So it's really meant to detect more like Jupiter-sized planets directly around other stars at Jupiter, Jupiter-Sun distances. So that's why it's a technology demonstration, where we're trying to show that we can do it, and then we'll build off of it, the success of this, hopefully, right, and then use even more of this and more refinement with higher technology versions of this in future missions. All right, so let's get to the science with Roman. What kind of science will Roman be able to do? The first is I want to point out that because it's a survey telescope, it's not going to do observations in, most of the observations won't be sort of the traditional way that, for example, Hubble and Webb do observations that are targeted. So the way that Hubble and Webb work are, right, that scientists write a proposal. They say, oh, I want, Hubble or Webb or whatever to look at this target for this much time, and because I have the science to do, right? Well, with this large field of view, you can do so much science by just doing these large surveys. And so instead, what's going to happen is the astronomy community, in fact, this process is just getting further refined now, but the astronomy community is going to come together to define around 3 primary surveys, and then I'll talk about a 4th option as well at the end. But the first primary survey is called this High Latitude Wide Area Survey. And essentially, this gives you an idea. The full moon is for scale there, and as you back out, this High Latitude Wide Area Survey will cover a potential area of about 2,000 square degrees. Now that is tremendous. I mean, if you think about Hubble quality data, but 2,000 square degrees, that is a lot of data, right? That is a lot of information. And so obviously to do that, if you remember that interesting shape for the camera, you have to take an image, move the telescope, take an image, move the telescope, and you sort of build up a picture over however big this potential survey area will be. But it'll be something like 2,000 square degrees in size. So that's the High Latitude Wide Area Survey. And the reason it's high latitude, what they mean by high latitude is high latitude out of the plane of our Milky Way galaxy. So this is a survey meant to get at galaxies, or be able to at least observe galaxies outside of our Milky Way, right? And it will enable us to sort of piece together a 3-dimensional picture of our universe, right? Where galaxies are located in space, position and distance and so on. And so that'll going to help us build sort of a big picture of space. But of course, 2,000 square degrees, you're going to capture a lot of other things in this survey as well. And then there's another core community survey where it will be a high latitude, but it will be time domain. So here, the interest is to capture the dynamic universe, things that sort of go off in the night that you might not expect. I think we're used to thinking about the universe, or at least a lot of people are used to thinking of the universe as a very static place, right? It's not changing; it's the same. When the truth is, it's very dynamic. Things are happening all the time on time scales of hours to days to weeks to months and so on. And the issue is, you wouldn't catch that if you're not taking repeated observations of the same patches of sky over and over and over again. And that's really what this survey will do. It will be, again, high latitude, so it can look at things past our own galaxy, but time domain, so we can catch things. Of course, some things that it will catch are represented in this sort of artist's illustration of type 1a supernovae. So supernovae, we've known about for a very long time. These are exploding stars, right? They've essentially reached the end of their life, or they've reached some certain threshold, right, of mass, and they explode. And we'll catch supernovae going off all throughout these time domain surveys. Another thing is we might catch, like what's on the right here. Here's a demonstration, if you see these little blips going off, of these really rare events called hypernovae. And these are cataclysmic events of compact objects, of like remnant stars and so on, colliding together, that are extremely energetic, but are also seemingly extremely rare because we don't catch them very often. In fact, there's only, I think, one. We've caught, we think, several, but there's only one confirmed, I think, hypernovae. Maybe that's gone up since I've looked at this, but they're very small numbers of these that we've actually caught. And these will tell us, you know, just hypernovae by themselves will tell us something about the energetic universe and where some of the heavy elements may come from in the universe and so on. But even more to the point, we might catch things that we aren't expecting at all, things that we would never have caught before. And you don't know what you're going to catch until you start looking. And this little display at the bottom here is really meant to be sort of a nominal supernova survey region. If you were looking for supernovae, the credit folks here that I put down here were interested in looking for supernovae, and so they came up with sort of a nominal idea for how they might stack the images and repeat the observations over time to try to catch supernovae. But like I mentioned before, these core surveys are just being defined now. They're being defined for catching time domain things generally, not just supernovae. And so the actual implementation of the survey is still to be decided. But in this nominal idea here, we're talking about 5 square degrees in the red sort of circle that are fully covered, and the blue circle an additional 3 square degrees. So it's very much a smaller area than the 2,000 square degrees that was the wide area survey. But again, it's getting at time domain. It's repeating the observations over and over again to catch things that are going off in the night sky that we would not have otherwise caught. By the way, what would be really cool about this too is with these time domain surveys, we're going to start being able to play movies of the universe, right? If you're doing this over several years, there are very interesting things that you can do in the time domain. You can actually watch as supernovae light echoes go out with time. You can watch as nebulae expand or change with time. So we're going to get some really interesting, essentially videos or movies of the universe.
How to kill all mosquitoes in the area in 90 seconds. This simple but brilliant trick you can do.
And then the last core community survey is this galactic bulge time domain. This is another time domain survey, but this time we're not avoiding the galaxy. We're looking directly in the center of the galaxy, which is what this animation on the left is trying to show, which is basically we're pointing right at the bulge of the Milky Way, right at the center. One of the reasons to do that, there are many reasons why you might want to do that, but one of the reasons that sort of got this sort of core community survey going, the interest was in finding exoplanets, and in particular, finding exoplanets or planets around other stars in a way that hasn't really been fully utilized before. So if you're familiar with the Kepler Space Telescope or the TESS Space Telescope, they find exoplanets by what's called the transit method, primarily, where as you stare at the stars, you might see a dip in the light over time because a planet may have crossed in front of the star. If the orientation of the planet in the star system is just right, a planet may have crossed in front of the star and dimmed the light. And then you can infer that there's a planet, right? And roughly the size and so on. Now that's really good for planets that are close to their star, right? Because planets that are close to the star will orbit their star much faster. And so there's more likelihood that you'll catch it passing in front of the star, and maybe even multiple times. But also the relative size of the planet and the star, because they're closer, are a little bit higher. So you'll get a little bit more light being blocked and so on. So it's a way of catching, it's better at catching those planets that are close to the star. That's why that method has caught so many planets that would be like within, for example, the orbit of Mercury in our own solar system, right? the technique Roman will use when it stares in a time domain survey at the galactic bulge is called microlensing, which is meant, and I'm going to play this and maybe pause it, but it's displayed in this visualization on the right. So before I hit play, I want to note that the Roman Nancy Grace Roman Space Telescope is here on the left of this visualization, and in the middle you'll see this planet, and actually that's not visible to us, right? We don't know it's there, right? That's what we're trying to detect. The planet's dim. You can't detect planets. You can't just detect planets like that, very easily, right? They're very dim. So we need another way to find out that it's there. And microlensing is that technique where the telescope is actually staring at all these background stars, like it's staring at this star back here. And as this planet passes between us and that background star, the light from that star will be bent just ever so slightly by the gravity of that intervening mystery planet. And what that looks like to us, it's almost like a funhouse mirror effect. What that looks like to us is we're actually seeing that star brighten and maybe even duplicate its appearance on the sky. So I'll hit play, and you can kind of see you'll see this. That's actually one star that appears to brighten and be two stars as the planet passes in between us. And so if we look at a whole field of stars and we monitor how their brightness changes, we will capture these microlensing events. And what's great about the microlensing events is it's going to allow us to build in the family picture of planets around other stars. The transit technique found these planets that are closer to their star predominantly. This microlensing technique works better for planets that are further from their star, at roughly Earth-Sun distance and beyond. So the colder planets. So we'll be able to build in the picture of how common are perhaps Earth-sized planets, how common are Jupiter-type planets, and so on, by these techniques. We're sort of building in the family portrait. I will say there's a lot of other science that will be done with this survey. By staring at stars, you'll learn a lot about the stars themselves. There's also the transit technique, which will still work in this survey, so you'll find planets that way as well. So this survey opens up a lot of scientific potential. And then the last, about 25% of Roman's time will be open for the astronomy community to propose additional surveys. And those additional surveys can cover all areas of astrophysics. And so what I put on the screen here are just some of the areas of astrophysics that Roman will address, from evolution of the universe, galaxies, mapping dark matter, how galaxies assemble, Milky Way structure, precision astrometry, which is actually measuring the positions of stars and how they move spatially on the sky, globular clusters, gravitational wave counterparts. So this is something called multi-messenger astronomy, but when we receive these mysterious gravitational waves from the universe, we can follow up and find them with Roman, or maybe Roman even finds them first in one of their images, and we go back and look at it. Astroseismology, so how stars, essentially star quakes, or how stars themselves, the motions of stars themselves and how they move. Planetary system diversity, so looking at our planetary system as well as other planetary systems and looking at how diverse they are. Again, direct imaging of exoplanets. Things in our solar system, like mapping the Kuiper Belt, the outer solar system, all those small icy bodies out there. Roman will be staring out and doing surveys. And of course, no matter where it stares, it has to, by definition, stare through our solar system. So it will be capturing lots of these things, just traveling around the Kuiper Belt and Oort cloud and so on.
Where does the poop go? Really? If someone's backed up and constipated for 2-3 days or even a week.
And then I'm just going to go through a few examples here of, and I want to be cognizant of time. So if I'm running a little long, just go ahead and let me know. But I did want to touch on a few specific.
Brandon, we're getting a lot of questions, and so we want to save at least 10 minutes and maybe a little bit more for for questions.
Okay, so do you think 10 minutes more? Is that?
Yeah.
Okay. Okay, great. So I'll rush, but I'll go through these a little quickly. But I wanted to walk through some more science cases. So planets by the thousands. So again, I talked a bit about this already, but there are so many exoplanets waiting to be discovered. And again, many exoplanets found so far are gas giants. Roman will discover how common smaller rocky planets are, how common or unusual our own solar system is compared with the rest of the galaxy. Roman will use the techniques of microlensing like I talked about. So that's I already talked about. We also have, of course, direct imaging. So here is actually a direct imaging from the Keck telescope on Earth of a 4 exoplanet system. So you'll actually, when I hit play, you can see a coronagraph has masked out the central star, so it looks dark, and they put a little star symbol in there so you know where it is. But that's not actually a picture, that's just a nice little symbol. But when you hit play, you can actually see these 4 blobs, 3 close and 1 further out, going around the star, right? And so Roman will have a next generation coronagraph, and we'll be able to do this to much greater detail. Of course, I mentioned our cosmic neighborhood. Here is our solar system with the sun in the center, and Roman will be pointing away from, Roman cannot, just like James Webb and Hubble, it cannot point towards the sun. That would not be good for the telescope. So it will be pointing away, but no matter which direction it points, by definition, it points out of the solar system. So we'll be capturing a lot of objects that are just going around the outer solar system and tracking and being able to pinpoint and locate them. Stars by the billions. Here's an example of what you can do with Roman. Again, you see these 18 squares. Those are the detectors that make up the camera in the Roman field, and 1 Roman pointing. So here's 1 Roman pointing in the Carina Nebula. And what I point out here in that blue rectangle is one of the largest mosaics that Hubble has ever taken. And that is a Hubble image, that large blue rectangle. It took Hubble many pointings to create that. And you can see in 1 Roman pointing, you get much more than that. And so in 1 snapshot, if you will, in 1 image with Roman, you get the entire life cycle of stars. You'll see in the Carina Nebula stellar birth, places where stars are being born. You'll find star clusters, regions where stars are born together, and you'll find stellar death like Eta Carinae, where stars are dying. You can find that all in just 1 image, let alone an entire survey with Roman. This is and I apologize if this is very bright on your screen, but I find it a very amazing image. This is actually a simulated image of what the core of our galaxy would look like with that 1 core community survey I mentioned. This is actually a simulated image of what Roman would see. So you even see the spikes on the bright stars, the 12 diffraction spikes. That's what the diffraction spikes from Roman will look like. Of course, we don't know exactly what the image will look like, but it's a simulated image to give us an idea of what to expect. Look how many stars are in this image. Right? Look at how many stars are in this image. It's there with this survey that we're talking about, over 200 million stars could be observed by Roman in this time variable survey. And what's even more amazing is when you look at this image to note that this image you see right here is actually 1/140th 1 Roman field of view. It's a tiny piece of a Roman field of view. Okay, so this is the kind of imagery we're going to get from Roman when we do things like looking at the center of our own Milky Way galaxy. All right, and then we can also look at stars in nearby galaxies. Here's the Andromeda Galaxy. And these are also simulated images of cutouts you see on the 3 cutouts on the right, where we sort of zoomed into regions. But you'll notice that we can actually start to really map giant galaxies like Andromeda, which is our nearest big galaxy to us. And it would only take, a handful of pointings from Roman to actually map out. And you can see individual stars in the Andromeda Galaxy when you do this. Just a note, Hubble did a map of a region of the Andromeda Galaxy, and hundreds of pointings to do that. And to get to what you can do with one Roman pointing here. All right, and moving on to galaxies, galaxies by the millions. Here's an example of what you could do. Here's another zoom in. Here's an image of what's been named Rubin's galaxy after Vera Rubin. It's a very large galaxy. It's fairly isolated. And this Hubble image you see in the white square in the center. And again, you see one Roman field of view with its 18 individual detectors acting as one camera. And what's great about this is, right, with one Hubble pointing, we can really get at, what's going on in the center of this galaxy. But really, galaxies, if you include all of a galaxy, are made up of more than that. And with Roman, you can actually reach out into the outskirts of these galaxies and understand what's going on in what's called the halo of these galaxies. What are the stars, gas, and dust that exist well beyond that small area that you see in the Hubble image, and start to understand how galaxies behave on larger scales. And then here's an image that gets at galaxy morphology, just noting that if you look at sort of a cluster of galaxies with Roman, you'll see all sorts of galaxies of different types of shapes, and we can really start to piece together how galaxies change with time, their morphologies, how they develop, their diversity, and so on. And then here's the famous, in blue, that little tiny square in blue is the famous Hubble Ultra Deep Field. That funny shape in white is all of Hubble's observations of that region. And then one pointing from Roman, right? You can see all of that. And so there is an interest of possibly doing sort of a deep field with Roman. That has been one idea that has been brought forth. And so you could see how much more of the universe you could see if you did a Roman deep field relative to a Hubble deep field. And then I will play this quickly, but just note that I didn't mention anything about spectroscopy, but Roman will also be able to do a spectrum of everything in its field of view. So here's a visualization of sort of the Hubble Ultra Deep Field like flying through, and you can get spectra of each individual galaxy. But what's amazing with Roman is it uses a kind of spectrograph that's called like a prism and a grism. It has a prism and a grism, but they both basically allow you to get a spectrum of every single thing in that field of view, right? So look at all of the spectra you'll get. So why are spectra great? Why do you want to look at the rainbow of colors of these galaxies? Well, by examining a galaxy spectrum, you can learn about its distance, the ages of its stars, star formation history, how many heavy chemical elements it contains, and more. So spectra really give you a great deal of information. A few slides on fundamental physics. This is probably the most complicated graphic that I have, but I will take a minute to explain it. It is one of Roman's big science mysteries, why it was sort of originally designed, and one of the science mysteries it's going to explore is dark energy, and what is causing the universe's expansion to accelerate with time. And one of the ways that we can get to that is by mapping the positions of galaxies with on the sky and with distance to sort of get the large scale structure of galaxies. And by mapping the large scale structures of galaxies and comparing it to things like the cosmic microwave background, which is the earliest view of our universe before there were galaxies, we can start to understand how dark energy works and the nature of dark energy. And so that's basically what this is trying to show. This is a simulation where all of those pink little dots, each little dot, which are too small to see individually on here, are an individual galaxy. And the idea is that Roman is going to be able to essentially do this work. It's going to map out the positions of individual galaxies in such a way that we can get that structure of the universe. And you're sort of, the way this graphic is, you're sort of looking back in time as you look away from Roman here. Of course, the mystery of dark energy will also be done by observing supernovae. So that's why supernovae are of such interest. Supernovae will allow us to track the expansion rate of the universe at different epochs in the universe's history. But I know we're running out of time, so I'll go through this quickly. The nature of dark matter is another big thing where when we observe large portions of the sky, we're going to see all these sort of what we call gravitational lensing events. Again, background objects, sort of their light doing funny tricks because the light gets bent by gravity, and most of the cause of that gravity on large scales is from dark matter. And so by looking at how light bends through the universe, we'll be able to actually map out dark matter and better figure out, where is it and what's going on there. And I just want to say, new physics, expect the unexpected. There are lots of things that we won't know, particularly with this time domain area of astrophysics, opening up the universe to seeing things in the dynamic universe. There's a lot to learn there. And I'm going to skip this, and I'm going to go to just one or two slides here at the end. If it hasn't struck you yet, hopefully it reaches you on this slide. This is a really big data mission. We are one of the challenges of the Roman mission, which is a good challenge to have, is we will have so much data. To give you some comparison, the first 30 years of Hubble, from 1990 to 2020, got us 172 terabytes of data. From the 5-year primary mission alone from Roman will get us 20,000 terabytes of data, right? So we're talking about having to employ new ways of understanding how to comb through that data, find what's interesting in the data. Astronomers need to find new techniques and so on.
Filing a simple return for free with TurboTax?
Woo, feels pretty good.
See if you qualify at TurboTax.com.
And I do want to end with sort of partners in exploration. Again, Roman is a survey telescope that has certain abilities that